On this homework, we'll be using the t-distribution. Now, it's very important we understand what exactly we are using. The t-distribution was invented by William Gossett, who worked for Guinness Beer. Now, he noticed that his intervals and tests weren't coming out correct, so what he did was he created a distribution based on degrees of freedom. If you take a look, the t-distribution right here is the one that's pressed down. Mr. T comes in with his fist and he presses down and says, "I'll pay the fool." With that in mind, the t-distribution is always pressed down more than the normal, which weights the tails heavier. When it has degrees of freedom, it rises up back into the normal. So it just wants to be normal. It'll never actually be normal. It gets more and more normal as it has more and more degrees of freedom. So you'll see similarities in some of these answers between the t-score and the z-score when we have a lot of degrees of freedom, because it'll rise up into the normal. And usually it's indistinguishable around 50 or so degrees of freedom, but it will never, ever, ever become the normal. It just gets closer and closer and closer. So it's all smashed down to start, and it rises up into the normal as it gets more degrees of freedom. For this chapter, we'll be using degrees of freedom n-1, which is sample size -1. Let's just go and look at some problems here. We need the critical value for a 99% confidence interval where the degrees of freedom are 14. So let's go over here to stat distributions. We want to create a 99% confidence interval, and I'm using stat distributions. Now, sometimes this won't give you enough decimal places, so if you need more decimal places, you will have to use David M. Lane. But one of the great things I like about this, you need to click the t-distribution if you're not on that distribution right now. So let's go ahead and type in the degrees of freedom right here, which were 14, and then we want a 99% confidence interval. 14 degrees of freedom. That means our sample size for a one sample t was 15. Now we want a 99% confidence interval, but I'm not entering that. I'm entering in 0.01, because if you notice, this has it on the outside. I can get the same answer by going right here and entering in 0.99. I can also get the same answer by going right here and entering in 0.995. In the tails on a 99% confidence interval is 0.005. So you can see the same thing on here. Even if I enter in 0.005, you'll notice all these answers have been the same. To make a 99% confidence interval, you would need to take half of the remaining alpha on the outside and put it into the tails. So let's do it the more traditional way and view it here. So over here on the side is 0.5%, and over here is 0.5%. And we should have enough decimal places, 2 decimal places, yay! So the critical value here is 2.98, it rounds up. Excellent. What is the critical value for a t with a 95% confidence interval for 61 degrees of freedom? Now I'm taking a guess here. We know that a 95% confidence interval is 1.96. Now the t has more variation in it, but after 50 degrees of freedom, it's going to be very close to the z. And so I'm using that understanding to take a guess, and am I right? I am right. That was a pure guess, and let's actually see it happen here. I believe there was 61 degrees of freedom, and we want a 95% confidence interval. So I might not have been exact. This will tell us the exact right here. So, whoops, t-value. Oh, it says the t-value is 2. Well, with the laws of rounding, I actually got close enough. But as we said, 1.96, and we can view that over here. Let's put in a 95% confidence interval, which is actually, funny enough, what we have right here. Go to 95%. And it's 1.96 on the z. And with the t, it's going to be actually 2, because the t has a little bit more area in the tails. So it's harder to actually reject tests, and your confidence intervals are wider, and I'm not displaying the right thing right here because of the degrees of freedom. Very, very important. If I put these degrees of freedom much higher, you will see it actually becomes the z. With more degrees of freedom, the t becomes the z. So fewer degrees of freedom, there's more area in the tails, and it's harder to reject, and as we add degrees of freedom, it becomes the z. So good stuff. Don't guess, just go ahead and get the correct answers by using the calculator, but understand the concepts of the z is just like the t, and the t is just like the z, except degrees of freedom. what is the p-value for t greater than 1.89 with 5 degrees of freedom? So to view that, we need to go over here. 5 degrees of freedom. We have greater than 1.89, and we need to do the right tail. Right there. 1.89 and greater than. So we are here on a t with 5 degrees of freedom. This will be labeled t and subscript 5. We can take a look. I've got some equations over here. This curve would be called a t curve with 5 degrees of freedom, and nope, we don't want that. It would look just like this, a t with 5 degrees of freedom. And you'll see that down here, that is n minus 1, and I believe that is correct. That is correct. N minus 1 is our degrees of freedom, and this is what we have here. It is a t with 5 degrees of freedom, and we are viewing the area under the curve above 1.89 for the test statistic. Good deal. The answer was very small, 0.059. And we have enough decimals. What is the p-value for? And this one gets people. It's 2.69 with 25 degrees of freedom. So we go over here to 2.69, and I believe it was 29 degrees of freedom? 25 degrees of freedom. 25 degrees of freedom, and we need to go on the outside of it. And here's why. Think about this. What satisfies this? Does negative a million satisfy it? Well, yeah, the absolute value of negative million is above this value. How about a million? Well, yeah, a million, the absolute value of it is above this value. How about 0? 0 doesn't satisfy it because 0, the absolute value, is not above this value. So as you can see on this graph, it's anything that would be below here because the absolute value would be above it, and anything above here because the absolute value would be above it. So we have a p-value of 0.013. That is the probability of observing these results. Make sure to follow these carefully. There are ways of doing these on the calculator with the t-CDF and the inverse t. I would suggest just practicing up with the David M. Lane applet. You will use the tests and intervals with your calculator, but for this point, use the applet. It's a great way. And if you have questions about the t-CDF or the inverse t, I will put those links in the description. A medical researcher measured the pulse rate, beats per minute, of a sample of randomly selected adults and found the following student t-based confidence interval. So this is really great right here, because we need to explain the interval in context. Every time in Stat 12 we start out, I am blank % confident that and we usually say this part next, that the true beats per minute, let's see here, that the true mean heart rate, let me put this in a very weird order for what I usually say. I am 95% confident that the true mean heart rate of individuals is contained in the interval 72.6 to 75.8 beats per minute. And this is just as fine right here, the ordering they've put it in. Usually we state our confidence level, what we are talking about, and then we give the interval itself. Very important, if you notice right here, they're talking about the true mean heart rate. That is so important. We're not talking about a proportion, we're not talking about a standard deviation. This is the true mean heart rate, and you can see it right here. We're estimating that the true mean heart rate is contained in this interval. Now the margin of error is always half the length of the interval, and you'll see that in the equation with the plus or minus. Right here for our interval, we have y bar, which is the sample mean, plus or minus some confidence level, and then times the standard error of y bar. The margin of error is everything after the plus or minus, so it would go up a certain amount and down a certain amount, so the whole length of the interval is twice the margin of error. To obtain the margin of error, we will take 75.811577 minus 72.570522 and divide by 2. What I've done is I've taken the upper and the lower and divided by 2. So take the upper point and the lower point, subtract them from each other, and then divide by 2. because that'll give you the distance they're apart when you subtract them, and then dividing by 2 gives you half that distance. So it wants to 1 decimal place. There we go. Half the length of the interval is the margin of error. If the researcher had calculated a 99% confidence interval, would the margin of error be larger or smaller? It will definitely be larger. Going from a 90, they calculated a 95, going to a 99 would increase the margin of error. Now we have to make our own 95% confidence interval. And the one thing that will really trip people up here is getting the t-statistic. So to get the t-statistic, we have to use technology, a table, or our calculator. So let's go ahead and use technology. With this in mind, there are 40 reduced sodium hot dogs tested. We want to make a 95% confidence interval. This means we will have close to 1.96, but not exactly. So going over here, we use 40 degrees of freedom, and we make a 95% confidence interval, but think for one moment. What do we get when we do it on the normal distribution when we have a 95% confidence interval? What do you think we would get on the t-distribution? We get 1.96 on the normal, so on the t, we will get something just a little bit bigger. This is a 95% confidence interval on a t-distribution with 40 degrees of freedom. 95% confidence interval, hence the middle of it has 95% shaded, and the tail is 2.5 and 2.5. And we have on a on a t distribution with 40 degrees of freedom. And I've made one mistake. I was thinking of the sample size. And if you notice the difference isn't too big, I don't know if the problem would actually catch you on that, but that was one little mistake that we caught before it spiraled out of control. Our degrees of freedom are n-1, and over here we can see the sample size is 40, and I should put in 39 as the degrees of freedom. This is for a one sample t. Now we have our t value here of 2.023. Let's look at our equations. To make our interval, we need to put in 2.023 right here. Next, we need to take the sample mean and put it in right over here at 301. Finally, we need to get the standard error of y bar, which is the sample standard deviation divided by the sample size. So the sample standard deviation is 35 divided by the square root of 40. You will plug that in right here. I suggest doing this by hand. Plug in all your numbers. What we can do is go to the calculator, your TI calculator, pause the video if you don't have it, and go to Stat, Tests, and we want to go to T interval. That's number 8. Under T interval, make sure Stats is selected. Now you won't see Y bar, you will see X bar. So for X bar, we need to enter in 301. For S sub X, it means standard deviation of the X variable, which is 35. Next, we put in the sample size of 40, and we want a 95% confidence interval. This will calculate our interval for us automatically. It just does all of the math instantaneously, and it carries out every decimal place. It is magical. Make sure you practice up with your calculator and practice up by hand. If you can work the formula by hand, you can then use the calculator to check your work. If your work comes out differently, you'll have to figure out which one to check. One note is on the test, we will give you the T star. We don't expect you to calculate it. We would tell you T star is this. What assumptions have you made? Our assumptions right here would be that, let's double check. It would be that they are selected independently and that the population of hot dogs weights is normal. Now I do have a slight qualm with that. Central limit theorem would suggest that the distribution of weights of the means would be normally distributed since we're taking means of 40. With this in mind, these other ones don't make as much sense, but I don't like that question so much. Is the randomization condition satisfied? Up here it says a nutrition lab test 40, so it doesn't really say. And I hate these questions. So let's see here. So we pretty much don't know. And I would say it's reasonable to think it is. It seems like they ran some sort of test. Good deal. These questions are not great. Is the 10% condition satisfied? Oh, yes. Sample less than 10% of all the hot dogs in the world? Wait. Oh, what? I'm not editing the video and taking that out. Let's see here. If you listen back, I actually said it. I'm getting to the last few questions, and I was like, yes, sample less than 10% of all the hot dogs. So I think that's one of the first mistakes I've made in these videos, and I'm keeping it in. It's the end of the semester, and yes, the 10% condition is sample less than. I saw yes, and I got all excited. Let that be a lesson to you. Double check. Just because you see yes doesn't mean it's right. Sample less than 10%. Is the nearly normal condition satisfied? Yes. With the 40 hot dogs, but since the sample 40 and we're going to say this, they should just have it as yes. But they're going to want this right here. There we go. My gosh, there's a lot of questions to this. And frankly, because of the central limit theorem, this should just be yes or no. The central limit theorem is going to tell us that the distribution of means is normally distributed, so yes. Explain clearly what your interval means. And we go back to our classic interpretation. I am 95% confident that the true sodium level of these hot dogs or the true mean sodium level of these hot dogs is contained in the interval 28.9 or 289.8 to 312.2. So we are 95% confident that the true mean sodium content in this type of random sodium hot dogs. Let's click there. Good deal. Well, congratulations. There's only 3 more homeworks left. Good luck.